Hi, I'm Shaozhang.
Hi, I'm Tianyang. In this video, we will give you a brief introduction to our final year project, AI Robotics. There are numbers of high abstraction topics in robotics-related study, which is hard for students to understand. Traditional education presented by textbook or whiteboard cannot present the 3D content clearly. Augmented reality is a tool which bridges the real and virtual world, benefit from its strong expressiveness. Real-time interaction and multiple platform support, this technology can provide opportunities to improve the interaction between the learners and learning materials, which produce more effective, active, and motivated learning.
The content presented by AI is in 3 dimensions. It's vivid, intuitive, which can help students to understand some abstract concepts visually. The visualization and the interactivity of AR make the teaching progress really attractive. As a result, enhancing students' willing to study. In addition, some results point out that AR has the potential to improve students' spatial thinking ability. Due to those reasons, we aim to develop an AR application that assists students in their studies of robotics about spatial description, transformation matrix, and depth and Hartenberg convention, aka DH notation.
This project is separated into 2 sections. The first section mainly contains 3D thinking training and spatial description through the transformation matrix, which is the fundamental knowledge of robotics. The second part is designed for learning of an important concept in the study of robotics, DH notation, which is a popular method developed for solving the forward or configuration transformation. Technically, we choose Unit 3D as the development engine. We use Vuforia, the AR software development kit, to enable the creation of AR applications on mobile devices. And Blender is our 3D modeling tool to polish the representation of abstract content.
Vuforia is an augmented reality SDK that enables app developers to create immersive AR experience. The Vuforia SDK leverages computer vision technology to identify and track image targets and 3D objects in real time. This functionality enables AR development agencies to orient and place virtual objects, including 3D models and the other content, in relation to the real-world environment. 3D models and digital information can then be overlaid on top of real-world scenes and viewed in relation to the environment through an AI-enabled smartphone or tablet. In the development, we use the image target feature of Vuforia. In brief, the basic working principle of it is Vuforia will convert the image into grayscale form and detect the feature points. After the image is saved into the database, when the camera captures an image has a similarity higher than a certain level, the engine will match the image with the original image in database. Unity 3D is our development engine. Unity 3D provides industry-leading developer experience combined with tools built for AR and VR creators and nominous VR and AR partners. With its intuitive and tools, Unity makes it easy to start a working prototype and bypassing time on low-level programming. We use Blender as our modeling tool. It is a free and open-source 3D creation suite. It supports the entire of the 3D pipeline: modeling, rigging, animation, simulation, and rendering.
Now, we will introduce the most significant content involved in our application, and followed by the development history for our user interface and user experience.
In spatial thinking part, user will be provided with a coordinate system model. Users need to rotate the model according to the given information. And through playing the animation in AR, user will know if they made the rotation correctly. The interaction between a real-world model and virtual environment can help students to improve their spatial thinking ability. This section provides an introduction about transformation magic, which is an important concept about spatial description to the users. As you can see, there are 2 coordinate systems which present users' input and the correct transform separately. Through comparison between the 2 coordinate systems, the user can get a feedback whether they have input a correct transformation or not. With the visualization of coordinate systems and transform, we hope users to get a deeper understanding on the meaning of transformation metrics.
DH notation is a very popular method to solve forward kinematic problems. In this section, we provide students with basic background information about DH notation, as well as the essential definitions. The definition of DH parameters are represented in animations. Each part of the animation represents the specific parameter, so that students can understand the specific geometric meaning of that parameter. The virtual representation of DH notation makes the invisible content more intuitive. At the end of this part, users are expected to have an enhanced understanding of DH notation. After understanding the concept of DH notation, we provide users with a specially designed exercise based on a real tutorial question from Unit TRC 4800 Robotics. In order to solve this kind of question, users are expected to set up a coordinate system on each joint. After that, users need to fill up a DH table. Instead of putting the exact value inside the table, we ask users to select the corresponding axis for that value. For example, A is the normal distance between the previous z-axis to the new z-axis. After conforming the selection, we can say if the answer is correct or not. The main purpose of this part is to show how the DH notation can be implemented in forward kinematics question. We hope with the help of AR technology, the concept of DH notation can be easier for students to understand.
After achieving the fundamental functionality of the application, our team spent more than one semester to improve the user interface and the user experience. In the following part, we will introduce some significant improvements in our application and discuss the consideration behind it. The instruction block has been added design background and border to make all instruction blocks look neat and uniform. Some arrow icons are made to lead the instruction block to the corresponding button. When we build up the model for coordinate system, the thickness of axes will increase to make it more visible. The end edge of the pink check is thinner to indicate the direction of rotation. The coordinate system before rotation is more transparent. What's more, the labels of axes are facing to the screen all the time. We render different colors for different links in the robotic arm to make users understand the structure of it better. To make the input field more user-friendly, there are two main modifications made. Firstly, the input field was separated into 16 individual input fields. This makes the input numbers look neatly arranged. Additionally, it is easy for users if they want to change one of the numbers. Secondly, bounce and highlight effects were made for the input field when it is chosen, to show users which blocks they are editing. When the application was tested on an Android device, we found that when the user pressed the input field, a default keyboard of Android would present. It blocked most of the screen and the way to input the number is too cumbersome. We imitate the number pad on the keyboard to create a mini keyboard shown in the right figure. The keyboard provides all basic functionality needed to import in the application. Additionally, when user click anywhere is not an input field, the keyboard will disappear automatically.
We asked one of the students who have finished Unit TRC 4800 before to try our application and gave some comments. In his first time using, although he had few questions on how to use the application, he understood the content and our aim of the project really fast. In general, he thought that it is a really good supporting tool which could help students to learn TRC 4800 better. Here is the feedback from him.
Well, after using the program, I think it's very useful for people studying robotics to visualize all the fundamental concepts like the DH notation. But then I guess if you let normal people who have no background in engineering to use this software, I think it'll be a bit overwhelming in terms of all the theory and stuff that's loaded into the application.
We also invited some students who don't have any background in robotics to test the application. They really enjoyed the AR experience and point out that the application is very interesting, and using AR to visualize some abstract content could be very helpful. However, the concept of DH notation is hard to understand in a short period of time, which makes it difficult to comment on how far the application can help students on this topic.
Okay, what I really like about this is I'm someone who really can't visualize things in my head, so when you're doing anything in a math class where they're like, okay, picture how something moves or changes, or even just picture a graph, it's just not there. So when you have something like this, it's really neat, especially to see different angles, to see how it changes. I think something like this would be really helpful in general for people to really understand the concept, how it visualizes, and how it actually applies, because you can kind of start learning about how you can make the numbers work out on paper, but you can really understand better when you can see how it works.
We also want to have feedback from someone who is authoritative in robotics. So, we visited lecture of Unit TRC 4800, Dr. Shaozhang. In the process, he seems to be very interested in our idea, and his comment is mostly positive. Also, he seemed to really like the 3D coordinate in particular. We asked him to try all our functions to see if there is anything incorrect or not clear enough. He also gave us some advice based on his own experience.
My general comment for Shaozhang and Tianyang's final year project is that the work is very noble and very practical as well. So this is excellent work. In my opinion, it is really good for demonstration. The user interface still need to be improved for this software can really be tested in theater. Need to be more user friendly. That's all my comments.
After evaluating those feedbacks, we realized that the subsection of the content in our application seems to have a relatively large gap for some of the students. From transformation matrix to DH notation, some students cannot understand the connection between those two concepts clearly. In the future, we can add some intermediate content so that students can have a smoother learning curve. In addition, we can cooperate with the lecture of Unit TRC 4800 to design a special tutorial which implements our application to support students. Subsequently, the capability of our application can be validated in terms of how far our application can help students in their study. Referring to the result, we can improve our application to make it fit the unit syllabus better.
In conclusion, we have finished all the functionality in the application, and the general feedback from different background students and the lecture of TRC 4800 is mostly positive. However, due to the time limitation, we cannot hold a rigorous experiment on the user's performance with and without the support of our application. But still, we think the goal of the project is achieved to the greatest extent. That's all of our project. Thanks for watching.